Hi everyone, this is Mondal from Stony Brook University. I am excited to talk about our model, Gazeformer, which offers scalable, effective, and fast gaze prediction for visual search. Gaze prediction for visual search involves predicting eye movements of a human searching for a target. Previous gaze prediction models have required for each target category gaze training data and detectors. Hence, these models do not scale well when gaze or detection annotation is unavailable. To this end, we first propose a novel zero-gaze task which evaluates scalability of gaze prediction models. We also propose a novel Gazeformer model to solve zero gaze. Gazeformer is more scalable, more effective, and faster than previous gaze prediction methods. Recently, gaze prediction models for visual search have been applied to multiple HCI applications such as augmented or virtual reality and robotics. Besides being accurate and fast, these models must be scalable. That is, they should extend to novel targets. This is necessary because collecting annotation for all possible targets is impractical and costly. As a result, we introduced the zero gaze task. This task tests the scalability of visual search models and essentially extends zero-shot learning to gaze prediction. Specifically for a training dataset with human scan paths for a set of n categories, under the conventional gaze train setting, the models are asked to search for a category within that fixed set. Whereas under the zero gaze setting, the model must search for a category outside that set. In order to solve the zero gaze problem, we propose a novel Gazeformer model which improves scalability, accuracy, and efficiency of gaze prediction. There are three key components of Gazeformer: language-based target encoding, transformer encoder-decoder architecture, and fixation modeling in continuous image space. In contrast to previous detector-reliant approaches, Gazeformer uses a pre-trained language model to encode the target name. This approach is scalable since it can encode any target, and additionally, semantic content of the linguistic embedding can help extend to unknown targets. Here we use a pre-trained language model such as Roberta to encode target category names to constant size embeddings. For example, we can create d-dimensional embeddings for car, sedan, and pizza cutter. For scanpath modeling, Gazeformer adopts a transformer encoder-decoder architecture. This model learns interactions between image and semantics of the target, and also models spatiotemporal context required for scanpath generation. In addition to encoding the target using a language model, Gazeformer uses a CNN backbone and transformer encoder to generate a contextual representation of the image. The image and target representations are then jointly embedded in the next step to endow image features with target semantics. Along with the joint visual semantic representation, the transformer decoder module operates on L fixation queries, where L is the maximum scan path length. The decoder then generates L latent vectors for final scan path prediction all at once. Previous gaze prediction methods have learned a probability distribution over image patches. However, this method does not penalize the actual distance between prediction and ground truth fixations, since all patches are considered to be discrete entities. Instead, we directly regress the fixation parameters of each fixation by sampling from Gaussian distributions using the reparameterization trick. Gazeformer also learns scanpath termination by predicting if a latent vector corresponds to a valid fixation or padding. Here we present the results of Gazeformer in two variants, without and with duration prediction as compared to other baseline models under the zero gaze setting on CocoSearch 18 dataset. Gazeformer outperforms other baselines on multiple metrics, thereby proving to be more scalable. Under the conventional gaze train setting on CocoSearch 18 dataset, Gazeformer again outperforms other baselines while exceeding human consistency scores on multiple metrics. This shows the effectiveness of Gazeformer. In addition to being more scalable and effective, Gazeformer is multiple times faster owing to its ability to generate an entire scan path in one pass. Here we show some qualitative results showing the generalizability of Gazeformer for target categories it has not been trained on. We find that Gazeformer manages to generate human-like scan paths despite not being trained on gaze data for fork and sink. In a more challenging setting, we ask Gazeformer to generate scan paths for synonyms or hyponyms of known target categories such as sedan instead of car or mug instead of cup. Because of the linguistic embeddings, Gazeformer robustly manages to generate reasonable scan paths. Gazeformer is also able to generate scan paths for uncommon target categories that are not annotated in COCO dataset, which is used to train object detector modules in previous gaze prediction methods. To sum it up, we introduced the zero gaze task to test scalability in scan path prediction and subsequently proposed a novel Gazeformer model to solve it. Gazeformer is not only more scalable but also more effective and efficient than previous methods. We hope Gazeformer will be extended to more visual tasks like visual question answering and be applied to real-world HCI applications. Thank you for listening.